what I'll call the big three convergence theorems. There'll be three important theorems in this class. These will be three important theorems in this class. There will be many more than three important theorems in this class. There already have been several important theorems. And they're all about proving that limits exist without knowing what the limit should be before. So right now, we have like one strategy to study limits, which we've used a lot. You prove that a limit exists by proving that it converges to a number. So what do you need to prove? You need to prove that for every epsilon bigger than 0, there exists a trace of big N such that for all little n bigger than big N. I guess it's too late now for me to ask that pop quiz again, isn't it? X sub n minus L is less than epsilon. So, right now, the way we have to study limits, like when I ask you to prove that, I don't know, 1 over n converge, there's natural guess. You know that it should be 0. Not because, like, I taught you how to see that it should be 0, but just like you thought about it for a second and you said, yeah, that's exactly as close to 0, now let's prove it. What if I give you a sequence that doesn't obviously converge to anything in particular, and has to use if it converges? You can't, like, process of elimination, each real number, ask if it converges there for every real number. Well, that's a lie. There are proof strategies to do that. You need to do something sneaky. You need to have some other trick. And that's what we'll develop today. So, here's the idea. So lots of things, some things that we'll do later on in the class. Step 1 will be prove that a sequence has a limit. You don't know what the limit is. You know it has one now. And then prove that the limit has to be something once you know it exists. But that's like slightly backwards from how we've done things in the past. You know what the limit should be, then you prove that that thing is the limit. So we're going to build techniques today that say there is a limit without requiring you to have a guess about what the limit is. And here's the first one of them. Monotone convergence. Let an be a bounded monotone sequence, where that one is underlined because it's not defined yet. Then a sub n converges. So if you have a sequence, it happens to be bounded and monotone, then you know that it converges. Here are the other two. This paragraph is slightly a lie. I think I'm going to delay doing the topology and do non-topological proofs of them. The first is the convergent subsequence theorem. Let an be a bounded sequence. Then an has a subsequence which converges. Where subsequence is another word that's not defined, but hopefully you have an idea of what that should mean. It's like a sequence that's contained in that sequence. We'll define it more formally later. And the Cauchy convergence theorem. Let a sub n be a sequence, then a sub n converges if and only if a sub n is Cauchy. Where Cauchy, again, is a term that is not defined yet. It's a powerful theorem, and we'll hit it in a bit. We will prove the monotone convergence theorem today. So in order to motivate this word monotone, let's just check this. So let's suppose that I erase the word monotone. Let a sub n be a bounded sequence, then a sub n converges. Is that theorem true? If it's not, then you're thinking of a counterexample. Can you think of a bounded sequence which fails to converge? Yeah. Negative 1 to the n does, right? What is a lower bound on negative 1 to the n? Yeah?
Is it negative 1?
Negative 1 or more. How many people would have said negative 2? You're also right. There are many lower bounds. What is an upper bound on negative 1 to the n? Yeah. Sorry. That sequence. Right, I guess 1 is an upper bound. So let's just, we're saying the things, let's just write them. Is the converse true? It turns out the answer is no. So if a sequence is convergent, then it's bounded. That's something that we proved last time. Let's disprove the converse. here is a counterexample, a sub n equal to -1 to the end. Is that sequence bounded? Yes. By -1 and 1. Or -2 and 2. Is that sequence convergent? Yeah, we proved that it fails to converge earlier, right? We said, well, let's suppose it had a limit. That limit would have to be real close to 1 and real close to -1. There's no number that's simultaneously really, really close to 1 and -1, so that's the contradiction. Is it convergent? No. So, is the converse to this stated proposition true? Yeah, we have a counterexample. We have a thing that's bounded but not convergent. Nonetheless, today I want to prove something that says something kind of like the converse to that thing is true. If a sequence is bounded and something, then it follows automatically that it converges. And that something will be the word monotone. And maybe I'll even, like, monotone is a word that you've probably heard before. What does monotone mean? We're about to define it, but I want to see if you just remember, yeah.
Like math terms or like speaking terms?
Math terms.
Oh, gotcha.
Okay. Well, it should be like mono is like the same or one. Like it should have some sort of behavior. So let's say what that behavior is. What if I say a sequence is increasing? What should it mean to say a sequence is increasing? Yeah.
The next unit of the sequence is larger than the previous unit of the sequence?
Sure.
As it goes?
And it should keep getting bigger or something.
Yeah.
A sequence is called increasing if for every natural number, a pair of natural numbers, n less than m, I'll write something which you might find offensive, x sub n less than or equal to x sub n. How many people would want like a strict inequality there? Sure. When I need one, then I'll say something like strictly increasing. Like it's weird. I would consider the constant sequence to be an increasing sequence. And the reason for that is anything that I can prove about an increasing sequence, I will be able to prove even if that's a less than or equal to. So I just want the most flexible definition that I can work with. Similarly, a sequence is decreasing if the same thing holds, except whenever little n is less than little m, the inequality is flipped. So there's like a single kind of behavior that a sequence might have for every natural number. A sequence is called increasing if it's always going up. If its only behavior is go up. A sequence is decreasing if its only behavior is go down. A sequence is monotone if either its only behavior is go up or its only behavior is go down. A monotone sequence is just an increasing sequence or a decreasing sequence. And that makes sense. Chances are if I can prove something for increasing sequences, I can prove that same something for decreasing sequences, so there's no need to... It's nice to have a single word for both. People feel okay about the definition? Yeah.
It's supposed to go in that blank then
Oh.
is that monotone supposed to go in?
Our goal today is to prove that if a sequence is bounded in monotone, then it is convolution. All right, so our goal is that theorem. You might tell by the theorem numbering that the other theorems will show up in a later section. So let's do this. So the first thing that I'll do is you gave me a different idea of what increasing should mean. Increasing should mean that like each one is bigger than the term immediately before. That's not quite what I wrote down. I said each term is bigger than all of the terms before that. What do you think? Do you believe that that's probably equivalent? Should be, but should we prove? Let us prove. Exercise 3.3.3. A sequence a sub n is increasing if and only if a sub k is less than or equal to a sub k plus 1 for every natural number k. And we'll use this exercise a lot without ever citing it. A lot of times if I want to prove that something is increasing, I'll just check that inequality if that's the result of the exercise. Let's try to prove it. So let's do the forward direction first. So let's assume that a sub n is increasing. And let's consider any k in the natural numbers. And maybe off to the side, just so I see how to motivate, what do I want to show? I want to show ak less than or equal to a sub k plus 1. All right. So, if the sequence is increasing and k is a natural number, why should that follow?
Why should I want to show follow?
Yes.
If we know that it's increasing, then we know that the next iteration is going to be larger than all the previous iterations, if that's a definition of increasing. So then, wouldn't we just know that by definition? Or by assumption, I guess, then?
So there's the definition of increase. Well, let's see. What I want is that, but where this is k and that's k plus 1. Are k and k plus 1 natural numbers? Is k less than k plus 1? Cool, let's write that down and then say, and so that happens because this thing is increasing. But you have to make sure to appeal to actually what the definition is. Until we have this claim, once we have this claim in place, then we will be able to be more flexible. So, let's see, as k is less than k plus 1, and k, comma, k plus 1 are both natural numbers, the definition of increasing concludes that ak less than or equal to a sub k plus 1. Groovy. That feel okay? Oh, yeah, sorry. All right, so let's do the other direction. So let's assume that ak less than or equal to a sub k plus 1 for all k in the natural numbers. We want to show for every n and m in the natural numbers, a sub n less than or equal to a sub m. And there's a hint there. The suggestion is like try induction. So let's try induction. So here's the framework that maybe I'll start with. So let's see. I need to prove something is true for every natural number, n and m. Well, maybe I'll start by just considering any n in n. And now let's induct on m. For a base case, let's set m equal to n plus 1. All right, so if m is set to be n plus 1, then how can you conclude that a sub n is less than or equal to a sub n? Yes. So let's consider any natural number n. Let us assume that little m is equal to little m plus 1. How can we show a sub n is less than or equal to a sub m? Yeah.
We just subtract 1 from both sides there, and then...
Sure, I think it's even easier than that. I know this is true for every natural number k.
Oh, such like m and n equal k.
So by assumption, a sub m equals a sub n plus 1 is bigger than or equal to a sub n. Fair enough. Right? It doesn't matter if it's called n or k. So what will we do next? We will now do the inductive step. Let's fix some m in the naturals. And let's assume a sub n is less than a sub m. Maybe it won't even be a natural number. It will be some m bigger than n. Assume a sub n is less than a sub n. And then what do we want to show in the inductive step? There's what we want to show. So, if I know that a sub k is less than or equal to a sub k plus 1 for every natural number k, and I know that a sub n is less than or equal to a sub m, how can I get a sub n to be less than or equal to a sub m plus 1? Yeah. Yeah, transitivity. So tell me the two things that you're combining transitivity with.
Well, I would, if I was writing it out, I would be using the fact that we've already proven that a sub k is less than or equal to a of k plus 1.
Mm-hmm.
And so, because of that, we know that a of m is less than or equal to a of m plus 1. And by transitivity, that would mean that a sub n is less than or equal to a of m plus 1.
Yeah, I know a sub n is less than or equal to a sub n because I get to assume it. My baseline assumption is a sub m is less than or equal to a sub m plus 1 because I know that for every k. So, by transitivity, let's see, I guess that means by induction for all m greater than or equal to, strictly greater than, n, a sub m is bigger than or equal to a sub n. People buy that proof? So we prove that it starts being true at m plus 1, at n plus 1, and then we prove that if it's true at m, it's true at m plus 1. So if it's true at m equals n plus 1, then it's true at m equals n plus 2. So it's true at m equals n plus 3, and so on. Groovy. So that was just like a sneaky application of induction. Any questions so far? All right. So here's the handy thing. If you now need to show that a sequence is increasing, you can either use the definition on the previous page, or you can check this condition. There's the payoff. So let's prove that a sequence is increasing. Okay, I guess I should say this. A sequence is decreasing if and only if that is true. So let's prove the following. Let's prove that x sub n equals 2 minus 1 over n is monotone. So what does it mean to be monotone? It's either increasing or decreasing. So we want to show either that the sequence is increasing or that the sequence is decreasing. It's probably not both. Let's try to decide whether it's probably increasing or probably decreasing by listing the first few terms. Do that in the margin as well. See, n equals 1, 2 minus 1 is 1, n equals 2, 2 minus 1/2 is 1.5. So is it possible that this sequence is decreasing? No. So I think we want to show that this sucker is increasing. Alright, so I think what I'll do is I'll like sketch the backwards version of the proof here, starting with the want to show and then getting down to something that's obviously true. So let's see, 2 minus 1 over n. We want to show that that is less than or equal to, okay, it doesn't matter what you call it, 2 minus 1 over k plus 1. There's what we need to show. I don't know. If you saw that in the wild and needed to prove it, do you think you could? Well, if you wanted to simplify that down to a truism, could you?
Possibly.
Yeah, let's try to do it. What would you want to do to this to simplify? Yeah.
Drag 2 from both sides?
Cool. Negative 1 over k less than or equal to negative 1 over k plus 1. I guess we're going up that way, so we'll be adding 2 to both sides at some step. Okay, keep on going. Yeah.
Multiply by negative 1 on both sides?
Multiply by negative 1 on both sides. I guess that will flip the inequality. 1 over k bigger than or equal to 1 over k plus 1. Okay, what do next? Yeah.
Take the inverse of both sides?
Sure. What will that do to an inequality?
Flip it.
Is that now something that is obviously true? Great, so we know where to start. So let's consider an ek. Then, well, it certainly is true that k is less than or equal to k plus 1. I also know that k is strictly less than k plus 1, but there's the thing that I actually need. How do you go from there to there?
Follow the algebra back.
Yeah, that's what I'm going to do. I'm just going to write the log. So I guess the first thing is inverting both sides. And there's actually some theorem that I'm citing right now, a theorem that I think you did in homework. Tells me that 1 over k is greater than or equal to 1 over k plus 1, negating results in the inequality negative 1 over k less than or equal to 1 over k plus 1. And finally, what do I need to do?
Add 2 to both sides?
Finally, add 2 to both sides to get 2 minus 1 over k less than or equal to 2 minus 1 over k plus 1. Thus, x sub n equals 2 minus 1 over n is increasing or decreasing? We proved something here. Awesome. Is increasing, and in particular is monotone. People feel pretty good so far? I guess I kind of moved that around so it slipped off the screen. People follow that proof okay? Yeah.
This might just be an inequalities thing I've since forgotten. But so if you invert both sides, it does flip the inequality. But if you were to multiply,
As long as everything inside is positive.
as long as everything inside is positive, okay. Then you can multiply the one side by like, so let's say k, and then multiply the other side by k to get 1 greater than or equal to k over k plus 1, and then it'll work out.
Yes, you could also do it by multiplying both sides by k and k plus 1. In fact, that's how you prove that.
Okay, and then if you go back again, and then you multiply that other side by k plus 1 and then over it. And then it flips it. Oh, yeah.
Good.
Right.
People happy? All right. In order to caution you about the order in which things are declared, I'm going to give a false proof of a statement that's obviously false. I want you to tell me why this proof is wrong. And the reason being that the result is false is not good enough. False proposition. The sequence negative 1 to the n is monotone. So I guess false things false. Is that obviously false? Yeah, it increases sometimes, it decreases sometimes, so it's not monotone. Let's see the proof. Let x sub n be negative 1 for the n. So far, so good. Let k be a natural number. Sounds right. By the trichotomy law, either x sub k is less than or equal to x sub k plus 1, or x sub k is greater than or equal to k plus 1. In the first case, x sub n is increasing. In the second case, x sub n is decreasing. Thus, x sub n is either increasing or decreasing, and so is monotone. What's wrong? Yeah.
Is that the correct use of the trichotomy law?
Is that the correct use of?
The trichotomy
law? The trichotomy law does say, well, it says that exactly one of the following is true. Either this is less than that, or they're equal, or one is bigger than or equal to the other.
Okay.
But that does follow from the trichotomy law.
Okay.
Yeah.
I think what he's trying to, I think what he's thinking about is like, I think of like the sort of, the circles and like the middle. We don't have the part where it can equal a certain number.
Oh, yeah, okay.
Yeah. So I know I think that's implied through what we're talking about, but it's not really stated.
Yeah, so there's a less than or equal to.
Yeah.
So that's like one of the bits in the sophos is being double counted.
Yeah.
But that's okay, yeah.
So can we just consider that k is a natural number, so k can't be equal to k plus 1?
K can't be equal to k plus 1.
So
Sure. I mean, it could be, right? The sequence could have constant bits. I mean, it doesn't. We know the sequence is negative 1 to the n. But if you know something strictly less, then you also know it's less than or equal to. So there's not an issue there. Let's try to write down this proof and see what it actually proves. So what did we do? We considered a new natural number k. So we proved, this proves for every natural number k, so we started with considering any k, either, so I'm going to put something in parentheses, x sub k less than or equal to x sub k plus 1, or x sub k bigger than or equal to x sub k plus 1. So that's what this claim proves. That's the proof that appears here. What's the definition of monotone? Definition of monotone is either increasing or decreasing. So let's expand out that definition. What does it mean to say a sequence? Well, let's just write it down. What does it mean to say a sequence is increasing? It means for all k, x sub k less than or equal to x sub k plus 1, or decreasing for all k, x sub k bigger than or equal to x sub k plus 1. Do you see how those two things are different? All right, so for all k, one of these two things happens is different from for all k, this thing happens, or for all k, that thing happens. Yeah. No, that's fine. So in fact, there's nothing false in the proof except for the conclusion. At no point does this proof actually do enough stuff to, well, I guess this line is also on. So in the first case, xn is increasing. What does it mean to be increasing though? It means for every k, x sub k is less than or equal to k plus 1. I haven't proved that. I've proven that for all k, x sub k is less than or equal to k plus 1, or x sub k is less than or equal to, no, greater than or equal to k plus 1. So for some k's, I have different behaviors, and this proof doesn't prevent that. So the takeaway is, make sure you're careful with your quantifiers when you're proving things like this. Yeah.
So essentially, the thing's proving that it increases or decreases, but inclusively here, not exclusively?
Yeah, and importantly, at different moments. It increases sometimes, or it decreases sometimes. But increasing means increases all of the time.
Okay.
Groovy. So, I think we're ready to get to the stage of actually writing down the monotone convergence theorem. And I lied a little bit at the beginning when I said, oh, it's really handy to have a way of getting a guess for what the limit should be, to know that something should converge without having to guess the limit. The proof of the monotone convergence theorem will come from a guess about what the limit should be, and then proving that that guess is correct. And let's motivate the guess. So I think here's the best picture on the next page. So there is a picture of a sequence which is increasing and bounded above. The dashed line, that dashed line is supposed to be the supremum of the set of all of these a sub n's. Does it look like that sequence is converging to that number? Yeah, all right. It looks like if I took like a reasonably small epsilon, so I build a little like epsilon tube around that. Well, that particular epsilon looks like a sub 5 gets into that little epsilon neighborhood. But then so do the rest of the terms have to be in there. So I think the supremum is what the limit of an increasing bounded sequence is. Intuition. If a sub n is increasing and bounded, then the limit of a sub n is the supremum of the set of all things that look like a sub n, where n is any natural number. Hopefully the picture is convincing anyway. Let's try to come up with a proof. And the proof, we can refer back to the picture to do some things too. So, we'll go through the proof of the second claim. The proof of the first. We'll prove the thing for increasing. The proof of the second claim, which is the same, but sup is replaced with inf, because of course it is. The proof will be exactly the same, with the exception of some inequalities will be flipped. So we'll prove the first one. I'll leave the second one to you, I believe, as homework. Let's do it. So let's let a sub n be a bounded increasing sequence. Let's let A be the supremum of that set of terms. And maybe we should say something here. I'm taking the supremum of a set. What types of sets have suprema? Yeah.
Bounded set?
Yes, but also non-empty bounded set. Is that set obviously non-empty? What's a thing in that set? Yeah.
The supremum?
Supremum is probably not in that set. Like a sub 1 is in the set, right? So it's easy to show it's not empty. A sub 1 is in it. Is that set bounded by bounded above basically by assumption? Yeah, suppose you had an upper bound on the sequence a sub n. Would that same thing be an upper bound on that set? Would it be bigger than everything in the set? Or all equal to maybe? Yeah, okay, so it is bounded above and non-empty, yeah.
Wait, so we were able to prove that it's non-empty essentially just by plugging in things from the definition?
Yep.
Like that it has an natural number, so we just plug in A1. So hey, we have an A1, so we're done.
Yeah,
Oh, okay.
non-empty just means there's something in there. I don't care what it is.
Okay.
It just needs to have something. You can also say, well, A5 is in the set.
Okay.
Cool. Often, non-empty is the easier thing to prove than bounded above. That's not always true. So let's let A be the supremum. I want to prove the sequence A sub n converges to A. And we've done this enough times where you have like the anatomy of how this proof should look. I need to consider any epsilon bigger than 0. I need to do some sorcery and come up with a choice of big N. Then I get to consider any little n bigger than big N. And I need to show that A sub little n minus A in absolute value is less than epsilon. So let's try to do that. And we'll refer to the picture up here. So let's consider any epsilon bigger than 0. And I'm going to try to come up with a choice of big N. Do you remember that reformulation of the supremum that had epsilons in it? Do you remember how the phraseology went?
Yeah.
Okay, let's fill it in. So, by the reformulation of the supremum in terms of an arbitrary epsilon, we see there is some element of the set, some a sub n in the set of all a sub n's, such that what happens? And there was a hand up.
It was like the supremum minus epsilon is less than that element.
Yeah. Oh, so notice, did I just also sneakily come up with a thing that I'm now calling big N? And let's just, in the picture, not that picture, because that picture is too crowded. See if we can make this, see if that seems reasonable. So there's an increasing sequence which is bounded above. There's the supremum, which is at that y value. There's a reasonably small epsilon 2. All of those lines are perfectly straight and parallel. I don't care what you tell me. So the statement there, so if there's the supremum, that's A. There's A minus epsilon. There's A plus epsilon. It looks like there's a choice of A sub n. If I now look at any little n bigger than big N, are all of those terms also in this little epsilon 2? Cool. So I think this will work out. That's not a proof, but I think it's convincing. All right, so I have a choice of big N. Now I get to consider any little n bigger than big N. Let's try to prove those lines. And let's do them one at a time. Why is A minus epsilon less than or equal to A sub n, A sub little n? Now let's start with this. Since little n is bigger than big N, and A sub n, the sequence, is increasing, what can you conclude? Between A sub big N and A sub little n, which one is bigger? Yeah.
A sub little n.
Awesome. I guess they might be equal. Do I already know A minus epsilon is less than A sub big N?
Wait, can you do that?
Do I already know the thing written in green on the previous line?
Oh, okay.
Yeah, because it's written in green on the previous line. So I guess by transitivity, A minus epsilon is less than A sub little n. Now let's look to the next line. In this picture, are all of the A sub n's less than or equal to A? I mean, they aren't, but that's because I failed to draw a straight line. They should be, though, right? Because what is A? The supremum. It's an upper bound on the set of all the terms. As A is an upper bound on the set of all things that look like A sub n, A sub n is less than or equal to A. Is it obvious that A is less than A plus 1? Is A obviously less than A plus epsilon?
Yes.
Yes, because epsilon is positive. So let's just put this together. Thus, A minus epsilon less than A sub n less than A plus epsilon. Let's manipulate that inequality, and let's remember what we want. There's the thing that we want. We want A sub n minus A, an absolute value, to be less than epsilon. So what would you want to do to turn the thing that we have into the thing we want?
that is U plus epsilon, or is that an A plus epsilon?
That is an A plus epsilon. The only U is the capital U in upper bound right now.
Okay.
Yes. Subtract an A from all of them. Thus, minus epsilon is less than A sub n minus A is less than epsilon. Cool. Yeah. Not the triangle inequality, but one of the properties of absolute value, and I'm not going to worry about citing the right one, by a property of absolute value. We get A sub n minus A is less than epsilon. And now let's just see if we actually did the job. Only in the proof did I consider any epsilon bigger than 0? I hope so. Yeah, there it is. Consider any epsilon bigger than 0. I then, in a sneaky way, came up with a choice of big N. I then considered any little n bigger than big N and proved this. Yeah, that's a proof of convergence. How does that proof feel? Pretty okay? Yeah.
I just have one question, because I know with absolute value you can go from that last line there to essentially the previous line. But how do we go back in the other direction if we don't know for a fact that the absolute value of A sub n minus A is less than epsilon? That,
So this is going to be a...
is it an if and only if statement? So
Yeah,
it's both
yeah.
ways? Oh.
So that's not the proof of why it is. That's just me telling you, well, we did that earlier, so I'm not going to do it right now.
Okay.
It is, though. You could prove it by going case-wise.
Okay.
Nice. All right. So we've already defined divergence to plus or minus infinity. But nonetheless, let's state it again, because I want to prove this consequence. So a sequence diverges to infinity, and we write A sub n diverges to infinity if, for every big M, there exists a big N such that for all little n bigger than big N, A sub n is bigger than big M. That's familiar, I hope. You remember that? Right, instead of getting close to L, this is getting close to infinity. What does it mean to get close to infinity? It means you're bigger than any really, really big number that I pick. Same thing for diverges to minus infinity. So here is a souped-up version of monotone convergence. It says, suppose you have a monotone sequence. But let's suppose that it didn't converge. Well, then it diverges. But it diverges in a very particular way. That's the only divergence that a monotone sequence is, the plus or minus infinity. So let's try to come up with a proof. We'll only work with increasing sequences. Let's suppose A sub n is increasing and does not converge, because that's what I get to assume in the theorem, I hope. I get to assume that the sequence can... You have a sequence, it's monotone but divergent. I need to prove that it diverges to infinity, and let's start with this. Let's prove that it is not bounded above. And let's go by contradiction. Let's suppose, for contradiction, that A sub n is bounded above. Well, if A sub n is bounded above, what does monotone convergence let you conclude? Well, I use the word monotone convergence as it's not that same page. Because like the one earlier has a slightly more ambiguous version. Do I have an increasing sequence? Is it bounded above? So what does monotone convergence conclude? That it converges. Is that a contradiction?
Yes.
because I assume it does not converge. This is a contradiction. That's not how you spell contradiction, but I'm not going to try to fix it. This is a contradiction since A sub n diverges by assumption. Cool. So I know that this sequence is not bounded above. Let's see what we can do with that. Can I flip to the next page? Okay. So the sequence is not bounded above. So the big result is no number that I write down can be an upper bound. All right, so think about what we need to prove. We need to prove for every m there exists a big N such that some stuff happens. So let's consider any big M. Could that number big M possibly be an upper bound on the terms of the sequence? What did we just argue? We argued that there are no upper bounds. So could this big M be an upper bound?
No.
No, there are no upper bounds. M cannot be an upper bound. So by negating the definition of upper bound, there is some A sub n in that set such that M is less than A sub big N. And maybe you see where I'm going to go now. There's my choice of big N. Let's now consider any little n bigger than big N and explain why A sub little n is bigger than big M. All right, so let's consider any little n bigger than big N. Then let's be more specific than monotonicity. This sequence is increasing, so A sub little n is bigger than A sub big N. But I already know A sub big N is bigger than big M. Is that enough to conclude that A sub little n is bigger than big M? Yeah, cool. All right, so let's just digest this. I considered any big M. I came up with the choice of big N. I considered any little n bigger than big M. I deduced that A sub n is bigger than big M. That means A sub n diverges to infinity. So, monotone sequences, even when they diverge, have fairly simple behavior. So the last result in this packet is the following. If you have any non-empty subset, which happens to be bounded above, then there exists a sequence of elements of that set, such that for every natural number n, x sub n is in that set. And secondly, x sub n converges to the supremum of that set. And instead of writing down the proof right now, I think what I'm going to do with my remaining minute is let's draw a picture of the proof. So let's suppose we have a subset of the real line. I don't know. There it is. There's the subset X. There's the supremum. If I go back to the supremum minus 1 over n, where n is a natural number, is there a thing in the set that is to the right of the supremum minus 1 over n?
Yes.
Let's call that x sub n. So here's the payoff. The idea of that proof is as follows. And then I guess we can use the squeeze theorem. What's the limit of this as n goes to infinity? The supremum. What's the limit of that as n goes to infinity? The supremum. There are no n's. So by the squeeze theorem, what can you tell me about the limit of x sub n? this
Get rid of it.
Yeah. So that's the whole proof. And the only reason I'm not doing it right now is because I'm over time now. Meditate on that a little bit. And I'm going